Start recording. Okay, so we are in the middle of a discussion on waves. Waves, I've defined for you guys. It's not what when you picture a wave, you're probably picturing it wrong. How we define a wave in physics is it's a net movement of energy without the net movement of a medium. And you're like, what does that actually mean? And that means energy is passing through the medium, and the medium could move. But if there's no net movement, what does that mean? If it does move, what do you mean? Okay.
The item that it's traveling through, it doesn't actually move.
But that's not true because we know we can watch the water move. So what does it mean if there's no net movement? So there is movement, but there's no net movement. What does that mean, Manuel?
Well, net is the difference of, so like the high is similar to low.
Right. So if there's no net movement, what that means is, actually I'll go all the way back to the beginning here. Without net movement means the medium returns to where it started. So the water might be calm, and then the wave travels through, the water goes up, the water goes down. Actually, water waves are more complicated than that. Water waves actually cause a swirling motion. But the object, or the individual water molecules themselves, after the wave has passed, are back where they started. So there's no net movement of.
So if the wave comes, it's like. Okay.
I'll show you a video. Water is
Particles of water.
slightly more complicated. Yeah, basically. The net movement.
You just ruined like my.
The net movement of the medium is 0. So they might have a huge movement one direction, but they will return to where they started, is the idea. We talked about mechanical waves. Mechanical waves require a medium. Things like sound waves, ocean waves require a medium. And then there's the electromagnetic waves. These ones do not require a medium. And I can think of far more examples of electromagnetic waves than we thought of mechanical waves. Examples of electromagnetic waves: X-rays. Keep going.
Radio station.
Radio waves. Gamma rays. And turn someone into the Hulk. Or wipe all life off a planet. Gamma rays.
Sun.
We'll call that visible light.
Cool.
Sorry? No, not stingrays. Stingrays are not electric. It's a good one. This, for those of you who are interested in this, and especially optics, this poster right here is the electromagnetic radiation spectrum. Everything we currently know about that spectrum and relative sizes of those waves. So, for example, visible light is on the order of, there's the visible spectrum right there. It's between the size of a bacteria and a virus. X-ray waves are roughly the same size as a water molecule.
That's one.
Microwave is actually an electromagnetic spectrum. The size of waves in a microwave are somewhere between a honeybee and a football.
Really?
Yeah.
What? Wait, what was that?
No,
You can't see them, but the wavelength, like the length of the wave. We'll talk about what wavelength is in a second.
like a football, like this or
The
like
size of the wave, the length of a football. Radio waves are just a little bit longer than a football field. And then we've got power lines in the human brain and all sorts of stuff. So if you're interested in, FM radio right there. Look at that.
what are
Right there. Look at that.
human brain waves?
What about
What are
they're very large.
Really?
Yeah. They're very large. Yes. Kind of. It's complicated. They can be detected. Yes. Okay. Well, that's what an EKG. Anyway, bringing back to this. So we've got mechanical waves. We've got electromagnetic waves. Electromagnetic waves do not require medium. Ultraviolet is just on the other side of visible light. So we got ultraviolet. Do I actually get into those? I don't think I do. That's okay. But like, so you've got the visible light is Roy G. Biv. If everyone's ever met Roy, red, orange, yellow, green, blue, indigo, violet, and this is in increasing wavelengths. We'll talk about what wavelength is here in a sec. But ultraviolet is after violet, and it's the violet as you leave the visible light spectrum. Now you can no longer see, but there is still a wavelength of light there. It's UV. There's UVA. There's UVB. And then on the short end here, what would make sense if red is on the longer end down here? What comes before red that you may have heard of? No. Infrared. I didn't hear you. Infrared. And as infrared light gets emitted as heat, it's radiating heat. For example, I'm very warm right now because I'm wearing a hoodie and this room is hot. So I'd be a bright light on an infrared camera right now. If you ever watched cop shows, there was this great one out of the UK that always followed this one helicopter around, and on the missions this helicopter went on, and you see everything's black, and there's that one little white dude just sprinting in the dark, just emitting lots of heat. And they're like, yeah, we see you way over there, kilometers away. He's emitting infrared because he's so warm. Against the cold everything else, the cold concrete. Yeah.
So like the video of the airport, a lady farts and you can see like.
Yeah. 100%.
The red thing.
Yeah. That's infrared. And electromagnetic waves do not require a medium because, interestingly enough, these things are all carried by photons, which are complicated and we're not going to get into.
Oh, come on.
No.
Just do something interesting.
It is, everything we've done is interesting. Photons are, as we've established, or we've attempted to establish, photons are massless particles that carry electromagnetic energy in the form of a particle or a wave. There's a wave. It's called the wave-particle duality. Sometimes they behave like particles. Sometimes they behave like waves. Depending, that's what photons are. This is light. Yes, we were talking about light. I lost it. It's gone. Depending on how you look at these things, it changes the nature of whether or not it's a particle or a wave. It's weird.
Hey, Mr. Rudolph?
Yes.
So, when the sun emits light, I know that's like the strongest light you can have, because it like lights everything up, but what about light like this? Light like that doesn't
about
go
light like that?
forever. Like, it doesn't go like...
Well, light from the sun doesn't go forever either.
Really? Okay. See, I don't know these things, so you gotta teach us.
Well, if you look up at the sky, there are sections of it that look black, right?
Well, yeah, that's because stars' light haven't reached Earth yet.
No, that's not what it means. That's not why.
Okay.
So Connor's asking actually a legitimate question. So Brendan and Jasmine, this poster right here is what's called the Hubble Deepest Field, or Hubble's Deepest Field. This is the Hubble Deep Field Telescope. We know what Hubble is, right? Giant radio telescope up in space, orbiting our planet. What they did was they pointed Hubble at an area of sky that was black. And they left it open for a while. And they just left it open to absorb whatever may be coming out of this blackness. And when they developed that image, that's what they got. So it has nothing to do with the fact that the light hasn't reached us yet, because it has. Each one of those is its own galaxy, never mind a star. The light is just so faint because it loses intensity as it travels. So, it's a cool poster. I quite like that poster. So, yeah.
Like, when I was a kid, like, I had this red light that you use to trick cats and other stuff. And my mother said to me that I can point this to an airplane. So what the airplane is meant to.
A laser?
Yeah, like a laser.
Yeah. Yeah, you don't
Like
do that.
that's true, like, you can really, not like make the plane fall, but
Well, you can.
you can.
Yeah.
Why?
Because planes are controlled by people and lasers blind people.
But it's like too far away. Or.
No, it's not. Lasers are very powerful. I had a laser at home. I think it's still at home. This particular laser that I bought off the internet, I could see it a kilometer away.
What?
It was a green laser that lasers aren't just nothing. Lasers are real dangerous. They can be real dangerous. It doesn't matter. Mine wasn't very big either. It was a $50. Again, it wasn't. You don't point lasers at people's eyes, and you can get arrested. I think it's a federal crime in North America for pointing a laser at a plane. Anyway, totally unrelated. Here we go. 3 more types of waves. The first one is this. We're going to talk about what's called a transverse wave. Okay, so a transverse wave. One sec, I can't read my own writing here. Yes. What did I write? Why did I write this? Okay, hold on. I can't read my own writing here. Come back. Why you gotta be that way? Okay, here we go.
Yes, I actually do.
No, I don't got it. I gotta look it up. Sorry, guys. Talk amongst yourselves for a second. Okay. Okay, so, and we're back. I can read my writing now. So, transverse waves. Before I show you what they look like, I'll tell you what they can travel through. Jasmine and Naya. Transverse waves are this particular kind of wave can travel through a vacuum. And solids. That's it. So it can either travel through nothing or it can travel through solids. It cannot travel through liquids or gases. And what happens in a transverse wave is this. The medium moves perpendicular to the wave direction. Okay, so here's what one of these guys looks like. Page. I'm going to use blue for this. So there's our transverse wave. I'll put a dotted line here right through the middle. This dotted line we call equilibrium. If the wave weren't traveling through whatever this medium is, it would rest at this orange line. And now there's some properties of waves that we're going to talk about as they relate to transverse waves. The first one, I think Manuel mentioned a few of these before. This distance from here to here has the same name as the distance from here to here. What do we call that? Starts with an A. You did. Pretty sure. We call this the amplitude. Maybe it wasn't Manuel. I thought it was Manuel.
I said the highest and no, I said the peak and the trough.
Oh, the peak and the trough. Okay. This point right here, we don't call it peak. We actually call it the crest. And we call this lowest piece down here, we call it the trough. And the distance from crest to crest, or from trough to trough, is what we call a wavelength. This guy down here is also a wavelength.
By the way, like whales emit waves too, like whales and dolphins. I think that they talk with waves.
And so do we.
Like
We measure really exactly like frequency.
It's just a different noise. It's the same way we're talking right now, except they're not transverse waves, because transverse waves only travel through vacuums and solids. Transverse waves don't travel through air or liquid, so these things can't be. That's the next kind we're looking at. So there's some variables that we use to represent amplitude and wavelength. Amplitude is represented by exactly the letter you'd expect. Big capital letter A, which also looks like amps. And wavelength is also what you'd expect. The Greek letter lambda.
What?
Looks like a little teeny tiny dinosaur there.
Looks like a 2.
Sure. It's not a 2, it's a lambda.
It's a 2.
There's another one down there. It's not a 2. How do you draw that? Start at the top and you curl up and then curl down and then you draw a leg. It's like the Greek letter lambda.
Nobody knows what the Greek letter lambda is.
It's that.
You know all the Greek letters.
I did at one point, yes. And half the Hebrew letters, because we use them in my classes too. So let's define some things here for you. Amplitude. You have a chance to practice lambda again. A is the max height / depth from equilibrium. And the wavelength, I'm going to draw another lambda, so I should do this one in red. Lambda is equal to, that's how we talk about the length of a wave. Measured from, okay, Summer, why are you guys in the hallway? Okay, can you close my door? Can you close my door? Close the door, please. Thank you. So loud. Measured from one wave to an identical spot. Happily. On the next. Okay, so that's how we define that. That's cool. So anything else to say about transverse waves? No, that's more or less it. Flip the page. That's the first kind of wave. Next kind of wave is called a longitudinal wave. I'll make sure I use the same kind of colors here. Number 2 is a longitudinal wave. There you go.
Wait, you just doing this on the white?
Sorry.
Say like you're thinking of putting like a whiteboard, would that consider like a treatment for a mental illness, or not? Would that just be putting them somewhere?
That's not going to put them somewhere. It's not really a treatment. Okay. Longitudinal waves can travel through liquids and gases and solids. It can travel through liquids. Got blurry. It is kind of blurry. Come on. There you go. And solids. They have a kind of an odd look to them. Make sure I draw this properly. The definition for these guys, I'll make sure I set it up the same way. For a longitudinal wave, the medium moves parallel to the wave direction. So I'm going to flip back here for a half sec because it just occurred to me that I didn't address one thing I wanted to address with our transverse wave. So the way I define a transverse wave is that the medium moves perpendicular to the wave. So in this drawing here, it is understood that the wave is moving which direction? To the right. Well, let's assume it's to the right. Could have been to the left. We don't know. So the wave moves this way, is to the right. But you can see the medium is moving perpendicular to it. It's moving up and down as the wave moves through it. On a longitudinal wave, the medium moves, should be an S there, parallel to the wave direction. And so there's a couple of different ways we could draw this. I'll use lines. So I'm going to draw some lines here. And then all of a sudden they're going to get closer together. They're going to get further apart. And then they're going to get closer together. And then they're going to get further apart. And then they're going to get closer together again. Santa's here?
Santa?
Santa's real? Didn't I tell you guys how Santa's dead?
Yeah, but we still don't believe you.
Okay. Hello, Santa. How to adjust the panther head? What do you mean? Yeah, put it on. There's no adjusting.
Oh, there's no adjusting?
No, it just goes on your head.
Oh, okay, so there's like Loki sliding.
It's a football helmet in there. It doesn't get adjusted.
That's what I was saying.
Okay. See you, Panther Claus. Okay, so you can see here, guys, there are sections of this thing. There are sections of this thing that are closer than others, and these guys get labeled similar to these other guys here. This section here, and this section here, and this section here. Oh, what am I doing? Is how we talk about amplitude. It's a little bit more convoluted to think about these ones, just because they look so much different. The amplitude, instead of it being up and down, the distance from equilibrium, the amplitude on a longitudinal wave refers to the closeness of compression. Wavelength was red. The wavelength is still the same. It's the length from one spot in a compression to the same spot in another one, or you can go from the least compression to the least compression. What else did I have on the other one? I had wavelength, amplitude. There's a little bit more we're going to add here. This piece right here, we've already talked about how these are a compression. There is, in the part where these things spread out, like over here where they are the most spread apart, the area of widest spread, we give that a name. We call that a rarefaction. Examples of longitudinal waves, especially for our area, earthquake waves are typically longitudinal. Actually, the ones that do the most damage are longitudinal. But there are also transverse earthquake waves, which is why earthquakes are so gnarly, because they have both. Interestingly enough, because transverse waves cannot travel through liquids, and longitudinal waves can travel through liquids, that's how we know what our Earth is made of. We know there has to be a liquid section somewhere, because there are earthquake waves that do not go all the way through our planet, but there are other earthquake waves that do, which means there's a section in there that's liquid. That's how we know that. So, fun fact. For those of you who aren't going to take earth science.
Mr. Buddha,
Yes.
about like a shock wave.
What about like a shock wave?
Yeah, for example, if a bomb goes off,
Yeah.
you get a shock wave after
Yeah.
that sometimes.
Typically, it's going to look like that's a longitudinal wave.
Okay.
Because again, transverse waves cannot travel through gases or liquids, but longitudinal waves can. So any wave that travels through a liquid or a gas has to, by definition, be a longitudinal wave. So you get like the shock wave from an explosion, or the fact that you can hear me speaking to you right now means that there are sections of the air that my vocal cords are compressing to varying degrees. The more compressed, the higher the pitch. The less compressed, the lower the pitch. But you can hear me. So those are longitudinal waves compressing the air that are vibrating little hairs in your ear that get converted into a nerve signal that go into your brain. Now you hear me. Yes, Connor?
What if you're using like a microphone and or like a walkie-talkie? You're talking into the walkie-talkie, and doesn't it convert the wave into a different kind of, or like one of the previous waves, as an electromagnetic wave or something, as it transfers through the other walkie-talkie? And then will that be like when it will it be the same kind of wave when it comes back out from the other walkie-talkie?
No, can't be the same kind of wave because your body's not designed to hear transverse waves. Those are electromagnetic. You can't hear electromagnetic waves.
No, but I mean like when it gets reconverted at the other walkie-talkie.
And it comes out as a longitudinal wave. That's how a speaker is built.
Okay.
So the speaker is just a big pad that vibrates up and down. As it pushes up, it compresses the air. As it pulls down, it spreads the air apart. As it thumps back and forth, it changes how the air gets compressed. Now you hear different sounds. That's the very simple premise behind how a speaker actually works. Turning electromagnetic wave signals into longitudinal waves that your ears can hear. That's a longitudinal wave. The last one is what's called a surface wave. Surface waves are wild, wacky, and complex. These things are neither longitudinal, I should spell that properly, nor transverse. Come on, Dweedoff, spell things today. They have their own little thing. These guys typically occur at the edge or surface of a medium. And so, I mean, that's why we call them surface waves. The best example I can give you of a wave that is a surface wave is a water wave. As at depth, as the energy, whatever it is traveling through the ocean, at depth they're longitudinal waves. It's a pressure wave, just traveling through the water. As at the surface, though, things get mucky, and as the depth of the ocean gets shallower, the waves, all of that energy gets compressed into a smaller area, and the wave actually slows down, creating these surface waves. And so you get a wave that ends up looking like this. And you get this crashing wave that we typically associate with the surface of the water. But what's happening in these waves, though, is if you look at a particle in these waves at the surface, what you'll notice is that within the wave itself, that particle actually travels in a circle. So something that's floating inside the water wave is gonna curl. We can model it. Show you a video. I have to pause the recording. So the best I could do is that model there, but I mean, I think that model does a pretty decent job. If you imagine like seeing something on the surface of the ocean, just kind of bobbing up and down, what it's doing is it's moving and it gets pushed forward and then pulled back as it rises and falls over the course of its progression. And the other interesting thing about a surface wave is a surface wave does actually cause objects themselves to move forward. Yeah?
You said that a wave moves energy without the net movement
Of the medium, yeah.
So, how does that work? Because I can also imagine, I think it's incorrect, but I can imagine particles moving up down as the wave moves.
Yep.
So, how do I?
Sorry? How is what?
Like, why is it moving up and going up?
Because that's the anatomy of the wave. I don't know how to answer. I honestly don't know how to answer that.
How is it a wave of
Net movement. And surface waves, again, the surface waves are an interesting one because if you look at the particles of the water that itself, as is in a surface wave, I mean, things obviously change as you get to shore, right? Because you got the crashing of the wave, and that totally disrupts the energy of the wave itself. But if you look at what the water's doing versus what a piece of garbage is doing, a piece of garbage isn't the medium. The water is the medium. So the water is moving in a circle here, but you might have an object on the surface that's actually moving forward. So that is a surface wave, causes this circular motion. It's both a compression and it's a transverse wave. I don't know, hopefully that helps a little bit, Manuel. The last concept here that I'm going to give you that I haven't yet, that relates to all of these different kinds of waves, is the speed at which waves travel. So wave speed is this last one we're going to talk about here. Wave speed is given to us It's the letter V, exactly as you'd expect it to be, V for velocity. And this is the rate at which energy is being transferred. Typically measured in meters per second, like all other velocities are. So what it is, it's v, the velocity, is equal to the number of wavelengths per time, and the time for one wavelength we call the, starts with a P, represented by big letter T. The period is the length of time for one wave. So the V is wavelength in meters divided by the period, which is in seconds. But that's not a super useful equation. The actual useful equation is this one. V is equal to the wavelength. We know that 1 over the period is actually equal to what? Sorry, yeah? Is frequency. So this is the equation that we use for waves. This is called the wave equation. The speed of the wave is equal to the wavelength times the frequency. Yay, Shiv, what's going on? I have no idea. That was Simmer and... With 20 minutes to go till lunchtime, now is not a great time to look for it? I have no idea. No, sorry, man. Sorry? Oh, well. Figuring this out on the Monday of your event is not a great time to do that. They had literal months to do this. Okay, so this is wavelength. Let's use this now. Flip the page. Let's look at how the wavelength equation actually works. Do a couple examples. Mr. McPhail. The wave equation.
I'd like to have some input, but I'm a chemistry guy, not a physics guy.
Oh.
It's been far too long.
Yes, clearly.
Is Angelina here?
Yes, she is.
Here for like 2 minutes?
Sure. Angelina, would you like to go with Mr. McPhail? No. I appreciate your honesty.
Hurts my feelings a little bit.
Okay, so let's do an example. A sound wave has a frequency of 192 hertz and travels the length of a football field, which is 91.4 meters, in 0.271 seconds. So just for fun, let's listen to what 192 hertz sounds like. 192 hertz. Sounds like this.
Is that like a perfect 192 hertz, or is that just kind of close?
This apparently is 192 hertz. Come on. It's not a bad one. This is 192 hertz. Okay, so that sound, we take it out to the gigantic sound system we had set up for Storm the Wall. We point it down the football field. We hit play. It takes 0.271 seconds for the wave to go from the speaker to the other end of the football field.
That's kind of a little bit longer.
How fast is that wave moving? What is the length of that wave? What is the period of that wave? And if the frequency changes to 442 hertz, which sounds like this, well, 442, not 432. Here's 442. Okay, so if it goes from that low one to this high one, what is the new wavelength and period? So, first we're going to figure out what the speed of that sound wave is. Let's go down here. Let's do it. A. How are we going to figure out how fast that wave's moving?
Wavelength times frequency.
We don't have the wavelength.
Okay.
So let's go conventionally. We know that that wave travels how far and how long? Yeah, we know that that wave's not accelerating, it's just traveling as it does. The distance that wave is traveling is 91.4 meters in 0.271 seconds. How fast is that wave traveling?
337.27 meters per second.
One more time.
337.27.
Okay, interestingly enough, this is approximately the speed of sound
So basically,
in
any
air.
wave-
In air. Okay, this is the speed of sound.
What is that?
So it's 300 to, the speed of sound in air is 300 to 340 meters per second. Depending on a few things, depending on the moisture level in the air, depending on the temperature of the air, and the speed of sound actually changes slightly. And why isn't it destroying anything? Well, it's because it's the sound that's moving. It's just the particles of, like the compression wave is bumping into molecules of air this fast. And so it's just these things bumping along each other. Where you get damage from things traveling at the speed of sound is when other things travel through that medium at the speed of sound. And so you get an F-14 or an F-18, these jets that can travel multiple times the speed of sound. And you can see the cone of air building up at the front of these planes. That's what causes this shock wave. Not that sound moving through air doesn't make a shock wave, because it is itself the shock wave. When you have other things that are trying to push through a medium, that's where they create a larger shock wave.
Understood. Yeah.
So that's the speed of this pulse. What is the wavelength of that pulse? So what we want to find here, we want to find wavelength, which is lambda. We want to know what that is. So what we're going to do here is what? What information do we have? What equation can we use to find the wavelength?
Well, we can find the frequency now.
We have the frequency.
Yeah.
Frequency is 192.
Yeah. So. Yeah. V equals lambda f.
So now we're going to use the wave equation. V equals lambda f. We know what V is. We know what F is. We can find the wavelength. So V we found to be 337.27. We're looking for lambda, and we know that the frequency is 192 hertz. So what's the wavelength then of that wave?
$1.76.
1.76 what? What are the units on that?
Lambdas?
They're not in lambdas.
I don't know.
Well, the speed was measured in meters per second, and my frequency is measured in
Oh, hertz.
reciprocal seconds. So my seconds are going to cancel, leaving me with meters. So the length of that pulse that compression wave is actually this long. You can measure it. As we make it louder or softer, what's that going to change on the wave? Do you think? Well, wavelength and like frequency determines the wavelength. Frequency is pitch. It's the note that you hear. If I change the amplitude, what do you think that's going to do to the sound? What's the only other thing that you can change on as you're listening to the sound?
The you know,
Sorry? Nope. So if I change the vibration, then I'm changing the pitch, which is changing the frequency. I leave the frequency the same when I change the amplitude. What's that going to do to the sound?
magnify, make it louder.
Make it louder. Absolutely. Yes. So this right here, the amplitude is related to the loudness. If this wave is sound. That's what we're talking about here. So, we have found the speed of the wave, we've found the wavelength of it. The period's going to be nice and easy. The period, how is period related to the information we already have here? One over the frequency. Cool. So the period of that wave is just going to be 1 over 192. So then what is the period of that wave? So this is the amount of time it takes one full wave pulse to travel past you. It's very quick. And then the last piece here, if the frequency changes from that low pitch to that high pitch, what does that do to the wavelength and the period? Or what is the new wavelength and period? So what do we know? What stays the same if the frequency changes? What do we not touch? The speed. Speed of sound is the speed of sound. That's not going to go anywhere. So the velocity hasn't changed. It's still 337.27 meters per second. But now what we're doing is we're changing the frequency. We're changing the frequency from 192 hertz up to 442 hertz. What's that going to do to the wavelength? Well, I'll manipulate this equation first. We know the wavelength is going to be equal to the velocity of the wave divided by the frequency. The velocity of my wave is 337.27. The frequency of my wave is now 442. What is that doing to my wavelength? Yep. 0.76 units.
No. Yes, meters.
It is meters. Thank you, Jasmine. So as the pitch increases, what does that do to the wavelength of the sound wave? The wavelength has decreased. It's gotten shorter. How about the period now? Well, that is easy. Period is equal to the 1 over the frequency is going to equal 1 over 442. What is that going to do to, what's the new period now? It was 0.0052 seconds. The period's now, James? 0.0023. We've more than doubled the frequency, so we're more than having the period. That makes sense. So now you can start, especially if you're into music or you are yourself a musician, you can start to see the relationship between the frequency of the sound and now we're bringing in the physics now, the frequency at which that wave is passing you. I'm going to give you some stuff to practice. I know there's about 10 minutes left in class. There's only a couple more days that we're going to do this, and then I'll give you guys a review for the unit. For the year, rather.
9 minutes left, but can't use zero.
Yes. I will allow that. Yes.
One sec, my Wi-Fi is working.
Okay, so the questions that I'm going to assign to you out of here. Let's do this. Which ones do I want to give you? We're skipping dishes. On the top ones, let's do the odd ones. So 1, 3, and 5. On the bottom ones, let's do the even ones. 2, 4, and 6.
Hey, Mr.
For question 6, you need the speed of light. The speed of light is given to you on the front of your formula sheet.
Shoot it off.
Yes, sir.
2 questions. On here,
Yeah.
right where it says wave equation, it says there, whatever you call the thing, it looks almost like an upside down Y. That looks more
It's a
like
lambda, yeah.
lambda.
That's,
Gotcha.
you're just,
Okay. And
just anecdotal.
my next question is,
Well,
so
first one was the question.
does each planet kind of have its own speed of sound based on its climate and conditions?
Every medium has its own speed of sound. Lots of posts to let you go. Is it an emergency, Harshawn? You can't wait 7 minutes? If
And
you can't hold it 7 minutes, you can go to the bathroom. I'll leave that up to you.
bonus question. What were the questions again? Number 6?
Pay attention, Connor. Odds on the first 6, evens on the second 6.